Welcome back to the lectures on Introduction to Multi-Agent Systems. In the previous lecture, we introduced the notion of Laplacian flows. We understood how Laplacian flows would actually be very intuitive in their design and can in fact also lead to consensus. Now, the question that arises is, while we do understand that the design of Laplacian flow is intuitive, can it actually be used to represent any real-world system? Which is something that we'll discuss in today's lecture. We'll take a look at a practical example of a system which can actually be designed using the Laplacian flows. So let's get started.
Consider a set of n agents distributed over a network, directed or undirected. It could be anything. Network G with vertex set B and edge set E. Let Xi denote the state of the ith agent. Our objective is to achieve consensus among the agents. Agents. What would consensus among the agents mean? It would mean that x1 is equal to x2 is equal to xn, meaning the states of all of the agents eventually become equal at some steady state. In other words, we can write it as this. Let X denote the state vector consisting of the states x1 going up to, xn. Then this lies in the span of the vector 1n. What is 1n? It is simply a vector of all ones. This is n cross 1. So the equation written here is exactly the same as the first equation. Okay, so this is now our objective. We have a set of n agents who are distributed over some network G, and we are interested, our objective here is to design a distributed algorithm or rule such that all of the agents achieve consensus with each other, meaning all of their states eventually achieve the same value. So what are the things that we already know? Let us consider a discrete time system. Then what is it that we already know? We know that if we now design a distributed process which evolves in this manner, xk plus 1 is equal to a times xk, where a is the adjacency matrix of G. Suppose this is my distributed averaging model. Eventually, under some conditions, on A. So what are the conditions? A has to be a, say, a primitive matrix. Or it has a set of or G has a set of globally reachable nodes which form an aperiodic subgraph. So these are the conditions that are required. So we say that eventually under some conditions, the agents are guaranteed to achieve consensus. Now let us look at a continuous time system. A continuous time system. We saw in the previous lecture that we can design an update rule which takes this form. X dot of t is equal to minus of the Laplacian matrix times x of t. Here, let us remember that L is the Laplacian matrix of G. We saw that under certain conditions, it definitely can lead to consensus. We saw a few examples. However, can we explicitly determine the exact conditions under which it is guaranteed that the system x dot of t being equal to minus lxt will always guarantee consensus? So let's write it. What we do not know so far, or what is our objective? Our objective is to answer a few questions. What are those questions? So this system, as we know, it's known as Laplacian flow. Now, the questions that we want to answer is, does the Laplacian flow drive all the agents towards consensus? The second question is, how are x dot equals minus Lx, which is the Laplacian flow, and xk plus 1 equals axk, which is the discrete time averaging process. How are both of them related to each other? So again, in this case, our main focus for the entire topic of Laplacian flows will be devoted, all of our attention and energy will be devoted towards figuring out the answer to this question. The second question, on the other hand, is an easier one. And I leave it as an exercise for all of the students to try by themselves. How can we show that x dot of t equals minus L of x, L times x? Let's also write the t here, x of t, and the averaging model, xk plus 1 equals ax of k. How are they related to each other? So the proof is not very difficult. So I encourage the students to try it by themselves and see if they can figure it out. If not, the answer to this question can be found in the reference textbook by Francisco Buller. Moving forward, let's now zoom in a little bit more on the Laplacian flow. So we already know by now that x dot equals minus of Lx. So let's write it a bit more. Precisely, x dot of t is equal to minus L of G, which is the underlying network, times x of t, gives us the Laplacian flow. The rate of change, or the time rate of change, of xi, which is the state of the ith agent, is given by xi dot of t is simply equal to the summation of j, where every j is an out neighbor of the ith node, is equal to, it's the summation over aij xj of t minus xi of t. So here the x is a vector. It's an n cross 1 vector. And what we've done here is we have written it for the ith component. And aij is simply the entries, the ijth entry of the adjacency matrix A. So this is what it looks like, component-wise. So what happens at steady state? At steady state, before we answer this question, let us first ask ourselves another question. Is there a practical system which can actually be governed by the Laplacian flow? Now, let's look at an example in order to answer that question. So let us consider a very simple circuit given like this. And we have a few capacitors here. And this is the ground. Again, we have two more nodes here. Let us add capacitors to them as well. And this is the last node. Let us now add some resistors to this network. Okay, so this is a system which consists of 5 resistances and 4 capacitors. So the idea is that the capacitors have some charge and they are driving some currents through the network. We already saw, we have in fact seen it twice already in 2 of the lectures, that we can model the current at each node using the Laplacian matrix. How can we do that? The answer to that question is this. We know that the vector of currents given by I is always equal to the Laplacian, which consists of the conductances in the system, times the vector of voltage is V. So V here is n cross 1 and I is also n cross 1. What is I here? I is nothing but the set of injected currents. And what is V? Sorry, instead of set, let's write it as vector. And V is a vector of potentials at every node, or the voltage at every node. So this is how we can model the current through the network, the current and voltage relation. Notice here that the capacitors here are trying to drive some currents through the network. Eventually, however, the current will get dissipated. But before it gets, before the currents get to zero, eventually we know that that's going to happen. But before that, how do we model the flow of current through the capacitors? Meaning, suppose we write them as C1, C2, C3, and C4, which are the value of the capacitances. Then it is well known that Ci dVi by dt. So we can correspondingly annotate the nodes as well. Say this is 1, this is 2, this is 3, and this node here is the 4th node. Then we can write C dV by dt is negative of the current injected at the ith node, meaning it is equal to minus I of small I. But what exactly is I? Okay. Now, before we can actually use this expression that is shown here, we must first convert it into a vector form. To do that, what we can do is, let us take the capacitance to the other side, and we can write this as being equal to dVi by dt is equal to 1 by Ci times I of I. And this relation holds for every I belonging to 1 to 4. Meaning, concisely, it can be written as d V1 by dt, dV2 by dt, or we can simply write up to d4 by dt is simply equal to minus of all of the 1 by Ci's can in fact be expressed as, let's write it as some matrix capital C, its inverse, where this matrix capital C is nothing but equal to a diagonal matrix whose diagonal entries are nothing but the capacitances present in the network. C4. And what does it get multiplied with? It gets multiplied with the current in the network, which is capital I. And what do we know from before? We know that capital I given here is L times V. Hence, in other words, what we can write is d by dt of some v of t is equal to minus of C inverse L times V of t, where what is V? V is nothing but the vector consisting of all of the voltages at all of the nodes. Hence, what do we see here? We have arrived at a system which takes this form. So let's try to understand what does C inverse L look like. C inverse L is equal to 1 by C1, 0, 0, 0, 0, 1 by C2, again 0s, 1 by C3, 0, and 1 by C4. What is the Laplacian? It looks like this. Let's write it as the degree here, degree of the first node, then minus A12 minus A13 minus of A14. Or rather, we should refrain it from writing the degree because the degree might include the self-loop term. Hence, we will just write it as L11, which is simply equal to the sum of A12, A13, and A14. Okay. The second term here is equal to A12, L22 minus A23 minus A24 minus A32, L33 minus A34 minus A41 minus A42 minus A43 and L44. Now when we multiply the two matrices, what we get is every term of the first row of the Laplacian actually now gets scaled. How? In this manner. We simply have the new matrix as, in the interest of time, let me first take this overall matrix and write it here. And now we'll modify all of the entries. Let's see, how do the entries get modified? Basically, all the entries of the first row get divided by C1. And the entries of the second row now get divided by C2. And similarly, the entries of the third row get divided by C3. And the entries of the fourth row get divided by C4. Notice that Interestingly, if we now multiply 1n to this matrix, we again get the 0 vector, meaning in this case as well, every row sum is actually equal to 0, meaning this C inverse L matrix also acts like a Laplacian matrix. It takes the form of a Laplacian matrix. What does this mean? It means that the system that we see here can be rewritten in this manner. dv by dt is equal to minus of some modified Laplacian L tilde times v of t. Or we can just omit v here. Effectively, this represents the model of a Laplacian flow. This is exactly a Laplacian flow. Meaning, we started with an electrical circuit as shown here. We were interested in studying the evolution or the rate of change of V with time. And what did we find? We find that the way V evolves over time is actually governed by a Laplacian flow system as shown here. Meaning Laplacian flows can indeed be used to model the behaviors of parameters in electrical networks. Meaning the Laplacian flows indeed can be meaningful, and hence we are interested in studying the emergent behaviors or the steady state behaviors which can be achieved using Laplacian flows. So let's quickly look at what happens at steady state. Can we make any general comments? To do that, let us start with the most general setup. So let's solution of Laplacian flows. Suppose this is a system. Okay, before we write this, let's quickly write what is the framework that we have. So consider a group of n agents interacting with each other over a network G, which has a vertex set V and an edge set E. Then the Laplacian flow is given by x dot of t is equal to minus L x of t. So what happens at steady state? Meaning, in order to study the steady state behavior, we'll try to explore what is the solution of this differential equation. So this is quite straightforward. What we do is, let us multiply e to the power lt on both sides. Minus e to the power lt times L xt. So we can rearrange the terms slightly to get, we can instead write this as a plus sign and this being equal to 0. this expression, in fact, can be further simplified a bit more. How? In this manner. Through this example, we see that the Laplacian flow can actually be used to model the behavior of a real-world system, meaning the Laplacian flow can actually be used to, in fact, even understand a system behavior a bit better. So with this, we will end today's lecture. In the next lecture, we will try to figure out how exactly can we determine the steady state behavior of a Laplacian flow system. And does it converge? Does it diverge? And what are the factors which decide the convergent or divergent properties of a Laplacian flow system? Thank you.